Hello, today we're looking at the volume of prisms. A definition of a prism is a three-dimensional shape that has the same cross-section throughout its entire height. One way to think about whether a shape is a prism or not is to think about a loaf of bread. And that is, can you slice the shape and get exactly the same slice all the way through? On this particular loaf of bread or prism, the height is measured from the front of the loaf of the bread to the very end. The volume of a prism is the area of a cross-section times the height of the prism. Now, volume is measured in cubes or cubic units, and the ones we seem to always use in Year 9 are cubic millimeters, cubic centimeters, cubic meters, and in very rare examples, cubic kilometers. Capacity is measured as a liquid, for example, milliliters, liters, kiloliters, and megaliters. Volume is a measurement of the amount of space that an object takes up. And as I said, it's measured in cubic units. Capacity is the amount that a container can hold. Now, some containers aren't full, as you know. When you buy a can of drink, they're not filled right to the top of liquid. So capacity is the amount the container can hold, whereas volume is actually the amount that is there. So a can of drink has volume because it takes up space, but it also has capacity because it can hold a certain amount of liquid. In this unit of measurement, we've looked at measuring distance, which is one dimension. We've looked at area, which is measured in two directions, usually length and breadth, sometimes height and length, but really there are two dimensions to remember. And finally, volume is measured in three dimensions. We usually have length and height and depth, three dimensions. Here we have an example from your book. It says converting units of volume. And we have to convert the following volume measurements into the units given in the brackets. So the first one is we're going from 2.5 meters cubed to centimeters cubed. I need some help here. Bring in my handy helper here, which gives me an easy way to convert units of volumes to one another. And this is interesting because look at the size that we have to divide by. The magnitude is much higher. So going from millimeters cubed or cubic millimeters to cubic centimeters, we divide by 1,000. Going up to cubic meters, divide by 1,000,000. Going up to cubic kilometers, we divide by 1 billion. Huge. And that's because we've just added in that other dimension of depth. Alright, remember that as you go from a smaller unit to a larger unit, we divide all the time, and going from a larger unit to a smaller unit, we multiply. With that said, let's have a look at the first question, A. So we're converting 2.5 cubic meters to centimeters cubed. Now remember, we're going from a larger unit to a smaller unit, so we're going to multiply. So we set it out like this. A 2.5 larger unit to a smaller unit, so we're going to multiply. So times, and because we're going from cubic meters to cubic centimeters, we're going to multiply by 1 million. So times 1 million. And our answer comes out to me, well, 2.5 times 1,000,000 is 2,500,000. And centimeters cubed. Let's have a look at B. Now with B, we're going from a smaller unit to a larger unit, so we're going to have to divide. So we write 4, 5, 8. Now we're going to divide. So here is, and we're going from cubic millimeters to cubic centimeters. So we're going to divide by 1,000. So we divide by 1,000. And when we do that, it becomes 0.458 cubic centimeters. Done. Alright, this is example 14, and the question asks us to find the volume of these three-dimensional objects. We suspect that they are prisms because that's what this part of the chapter is about, but let's just check and make sure. Are each of these shapes prisms? Do they have the same cross-section throughout the entire height of the prism? Well, let's look at the first one. The first one has this cross-section across here, and that, if you slice this each way through here, my slicing's not very good, but if we sliced it all the way through, we would have that cross-section extending all the way down through this prism. But if we had a look at it another way, the interesting thing about rectangular prisms, which is what this is, they have more than one cross-section. They have two cross-sections. So we found this top cross-section. The other cross-section is here. Whoa, did I say that rectangular prisms can have two cross-sections? Well, actually they can have up to three. And this one here, we've got this side here, which is also a cross-section. We can, if we sliced all the way down here through that, we would have a prism as well. So that's another cross-section. So rectangular prisms can have up to three different cross-sections. Let's have a look at this shape over here. Well, yeah, it's a prism, but it's got this odd-shaped cross-section here. And if we sliced through here, we would get that same shape all the way through. So definitely a prism. And this last one over here is a triangular prism because there's a cross section there, and that shape is all the way through. All the way through. Okay, so it's a prism. Remember that the volume of any prism is the area of the cross section times the height of the prism. Well, what's the height of these prisms? Looking at the first one, well, we could have the height going from here to here, which would make sense because it does look like height. But equally, depending on what cross section we could have, it could be going from the front to the back as the height, or across here, that could be the height as well. Let's have a look at the other shape and see where the height is. So this is our peculiar cross section shape, three-dimensional shape, and there's a prism, and the height is from there down to there, so it's 5 centimeters. And the height on this one, okay, be careful, the height is the distance from one cross section, the start of the cross section, right through to the end. In this case, the height is 6 centimeters. Now I'm going to solve these. Let's start with A. Alright, so we always start off by writing V equals area of the cross section times the height of the prism. Now I'm putting capital H there, and I'll show you why that's important when we get up to this triangular prism up here. So this one here, the volume is equal to the area of the cross section. Well, the cross section here we're going to use is this shape at the bottom, which happens to be a square. We're not entirely sure, but we think it is because it's meant to be a square. So the volume is the area, which is side squared for a square, times the height of the prism. And we fill that out, and we get 1 squared times 3, and our solution comes out to be 3 cubic centimeters. Now when we have a look at B, volume equals area times the height. Now this one here, the area of the cross section is given to us, so we write down V equals 10 times the height. Now the height in this case is 5, so it's going to be equal to 50 cubic centimeters. And now we're up to C. Now this is a triangular prism, and once again volume equals area of the cross section times the height. Now the area of this cross section, it's a triangle, okay? So we've got to remember that is a terrible triangle. Okay, there's our triangle. We've got to remember that the area of a triangle, area, equals 1/2 times the base times the height. Now the height on this triangle is given to us here. It says 3 centimeters, so that distance there is 3 centimeters, and the base is from there to there is 4 centimeters. So we write that in there, and we write down V equals 1/2 times the base times the height. Now this is why I've used a capital H, times the height of the prism. Okay, now we solve that. Equals 1/2, base is 4 times 4, height is 3, and the height of the prism is this distance here, 6. We solve that and we get 36 centimeters cubed, and then you're all done.